Now we are going to discuss what is a torsional pendulum theory. Here, the right-hand side diagram, if you are showing, if you are seeing that, it will show the torsional pendulum setup. The one end is fixed. The other end of the wire is connected to the center of the circular disc. This circular disc, we are just giving the torque. So if you are twisting the circular disc, it will execute the torsional oscillation. We found the previous lecture what is the time period of the torsional oscillation or torsional pendulum. So okay, time period of uh, the torsional pendulum. So t equal to 2 pi square root of the moment of inertia of the disk times the couple per unit twist. So this is the time period of oscillation. This time period of oscillation we can measure. So how you can measure it means, suppose you have to take the stopwatch, then you have to twist the bottom disk, so it will execute the small oscillation. So you need to find the oscillation for the 20 time period of the oscillation for the 20 oscillation. So you need to find the period, the t, for 20 oscillation. So you need to just figure out 20 oscillation, what is the time taken for by the torsional pendulum. Then you can determine the per unit oscillation what is the time taken by the torsional pendulum. So how you can draw the you can just plot the setup here, then you have to tabulate the value. Initially, the serial number, the first column, you have to take the first trial, second trial, third trial, fourth trial, as well as the fifth trial. Maybe you can repeat the experiment 5 times. Before that, you need to fix the length of the wire. Maybe around you can fix 50 to 80 centimeter. So better, if you want a better result, you can fix it 50 to 70 centimeter. Any one of the length you can choose, you can fix it. Then you got to give the twist for the disc. Then if you are giving the twist, you need to start your stopwatch. You got to count the time period, the time taken for 20 oscillation. So just you need to take the time period. Suppose if it is giving some quantity t1 time period, this is t2, this is t3, this is t4, this is t5, then you can count the time period for one oscillation, or the time taken by the torsional pendulum by Tp for one oscillation. So here you have to suppose if you are making 20 oscillation, then T1 by 20. Here the time period, if it is T2 for the second trial, then it's a T2 by 20. Third trial, if it is T3, then T3 by 20. It will go on. So you can repeat 5 or 10 times. That is for better result. You can repeat more number of times this experiment. So you need to take the mean for this result. Suppose if you are taking 5 results, then you have to sum up this 5 answer, then you have to divide it by 5. That is called the mean time period. So experimentally, you can determine the time period of oscillation of the torsional pendulum. Now, from the theory, we know what is a time period. This time period is equal to 2 pi square root of I by C. If you are squaring on both side of the equation, it will give t square is equal to 4 pi square. If you are squaring this square root, it will square root, it will get cancelled. It will give the moment of inertia of the disk divided by the couple per unit twist. So now you can determine the so you can just substitute the couple per unit test in this equation. The couple per unit test equal to the rigidity modulus time pi times r to the power 4, the radius of the wire power 4 divided by 2 times the length of the wire. If you are substituting this value here, what it will do? It will be t square equal to 4 pi square times the moment of inertia of the disk divided by the rigidity modulus of the wire times pi times the radius of the wire power 4 divided by 2L. So if you are rearranging this one, just you need to bring the n one side, the moment of inertia of the disk, sorry, moment of inertia of the disk is here. Then the n means the rigidity modulus of the wire, because we want to determine what is the rigidity modulus of the wire. So if you are bringing to this side, it will goes to the numerator, then t square goes to the denominator to the right hand side. So 4 pi square, the moment of inertia of the disk, times the 2L, because the denominator of fraction 2L goes to the numerator, 2 times L divided by the pi r to the power 4. If you are simplifying this expression, the pi, 1 pi, it will get cancelled. 2 fours are 8 pi I L divided by r to the power 4. This is a rigidity modulus of the wire. The unit for the rigidity modulus of the wire, already we know, it's a Newton per meter square. So here actually the time period of oscillations are measured in the unit of seconds. So this is a way you can determine the rigidity modulus of the wire. But there is another way you can just compute the torsional using the torsional oscillation. Then again you can determine what is the rigidity modulus of the wire, then the moment of inertia of the unknown object. So that is the thing we are going to discuss in the next lecture. So in this class, we are going to calculate the moment of inertia of the disk and then rigidity modulus of a thin wire using the torsional pendulum theory. This is the thing we are going to discuss. First, we will discuss about that the moment of inertia of the disk, the first part of the experiment, how we can calculate moment of inertia of the disk. Because given disk, we know the mass of the disk is m once. So if you know the given mass of the disk is equal to m kilogram. Then if you know the radius of the disk, suppose the radius we are calling from the center to the edge distance, because the circular disk, that's radius. The mass of the disk is capital M. So the radius of the disk is equal to or meter. We want to write it in terms of SI unit. Once if you know these two values, we know the theoretical how we have to calculate the moment of inertia of the disk. So the moment of inertia of the disk is equal to, in general, we are putting the symbol for the moment of inertia. It's I, that is equal to the mass of the disk time the radius square divided by 2. This is a theoretical calculation. The unit of the moment of inertia is kilogram meter square. But using the torsional pendulum, how we can calculate the moment of inertia? That is the question we want to answer it here. So what we are going to take, we are going to use the theory. Already we derived the period of oscillation of the torsional pendulum, the period of oscillation of torsional pendulum Tp equal to the, usually we are representing the period by T, it is equal to 2 pi the constant times square root of the moment of inertia of the disk or the system divided by the couple per unit twist. This is a way we can just calculate what is the period of oscillation of the torsional pendulum. Now this experiment consists of three parts. The first part is without any masses placing above the disk. That means the empty disk we are going to oscillate. The next part of the experiment consists there are two equal masses we are placing near to the axis of the disk. Then we go to oscillate. The third part of the experiment we are placing the same two masses far away from the axis of the disk. We are just placing the masses above the disk only. So that is third part of the experiment. We are going to calculate what is the time period of oscillation. Suppose here the first part of the experiment we are calling it's A without any masses, the time period of oscillation we are calling the time period of oscillations is T naught, the without any masses. That means it's a empty disk we are going to oscillate. The without any the disk won't have any extra mass. So that is without any masses above the disk. The time period of oscillation just we have to oscillate for 20 oscillation. We have to repeat 6 or 10 times. So for 20 oscillation, if you are repeating 10 times, we can find the what is the period of oscillation. The average value of the or mean values of the period of oscillation we are telling that is a T naught is equal to 2 pi square root of the moment of inertia of the disk without any masses you are calling that moment of inertia is I naught divided by the couple per unit is. Now, if you are taking square on both sides, the T naught square it will be equal to 4 pi square bracket the moment of inertia of the empty disk divided by the couple per unit is. So this is the thing we are getting. Now we are just placing the equal masses. Now we know what is the time period of oscillation. We have to put the tabular column like that. Now, using this tabular column, we can find what is the time taken for the torsional pendulum without any masses. That means we are just twisting or giving the twist to the torsional pendulum, then it will oscillate. So we are keep that 20 oscillation, then we are measuring the time period of 20 oscillation. That trial is T1. So how we can calculate the time period of our one oscillation means we got to divide this time period T1 by 20. It will give the time period for the one oscillation. This experiment we got to repeat for 5 trial. Up to 5 trials if you are repeating, it will give for the second trial, it will give the time period, it will be T2. The for one oscillation it will be T2 by 20. Again we go to repeat the same experiment T3, it will give T3 by 20. So you have to repeat it for 5 times. You have to take the average value, that will be T naught, the time taken for the by the torsional pendulum or the period of oscillation for the torsional pendulum without adding any masses. Now, the same torsional pendulum, the second part of the experiment, what we are going to do, we are going to take the same torsional pendulum with adding two equal masses from the axis of the wire. They are placing at equal distance, a d1 distance. So, with uh, the period of oscillation, period of oscillation of torsional pendulum TP with two equal masses, two equal masses placed at a distance d1 meter from the center of the disk or axis of the wire, from the axis of the wire diametrically opposite to each other. Now we have to repeat this experiment. We have to draw the same tabular column. We have to repeat the same experiment. That means we have to put the two equal masses. Here 50 gram, here 50 gram. So the distance from the axis of the wire or center of the disk, this is d1. If this is d1, then this is also d1. The mass of the small object, it will be small m. It is also, they are two equal masses separated by the same equal distance diametrically opposite to each other. Now if you are calculating the, again you have to repeat this experiment, you have to draw the same tabular column, you have to fill up the value. If you are calculating the time period for this configuration, the time period will be equal to T1. So just you need to put the T1 is equal to, so T1 equal to 2 pi, again to nothing going to change the constant value square root of, but the moment of inertia now it will be changed into I1, the new moment of inertia with the two equal masses. The couple per unit twist, it's depend on the wire, so it won't change. Now what is this new moment of inertia? The new moment of inertia I1 for this configured setup is equal to, it's a empty disk moment of inertia, that is I naught, plus the moment of inertia of the object, the small mass about its own axis, because you can draw the axis here. Here you can draw this axis for these two objects. So about this axis, what is the moment of inertia means? Small I. There are two objects, so you got to just twice it, plus you have to use the parallel axis theorem, because the small mass is placed from the principal axis at a distance d1. You have to use the parallel axis theorem, so that will tells us the mass time the distance square. This is a parallel axis theorem. Now we are placing two masses diametrically opposite to each other at a distance d1. This is also d1, the masses are same, so you have to twice it. This is a new moment of inertia of the system. Now we have to substitute this value in T1. Just you have to substitute this value in T1. Suppose if you are substituting this value in T1, that T1 it will be equal to 2 pi square root of, you have to just extend the length. The I1, the numerator I1, it will be I naught plus 2 times the moment of inertia of the individual object according to the parallel axis theorem, 2m d1 square divided by the couple per unit is c. Now what you have to do, you have to take the square on both sides, so it will give t1 square is equal to the constant 4 pi square, square root, it will get cancelled, it will give I naught plus 2 times I plus 2m d1 square whole divided by the couple per unit twist. This is the time period of the oscillation of the torsional pendulum when we are placing the equal masses at a distance d1. Now again we are going to repeat this same experiment. What we are going to do means, so here, yes, we are going to repeat this experiment. We are just going to place the two equal masses at a distance d2. So the third one, uh, the moment of inertia of the system or the time period of, we are going to repeat this experiment for the time period of oscillation of torsional pendulum when we place two equal masses at a distance d2. Now we are going to place the distance d2. What is the period of oscillation? Again, you have to draw the same tabular column. You have to repeat the experiment, but where you got to place the objects means you got to just place it far away from the center of the axis. You can place one mass, small mass is here, the another small mass is at the edge. This another small mass. The distance from the center, it will be d2. This object also placed diametrically opposite to the another small mass object. Its distance also from the center, it's a t2. Now one can ask what is the time period of oscillation. You can measure the time period, that will be t2. It will give 2 pi. Now for this configuration, again the moment of inertia will be different because the distance got moved. So parallel axis theorem, if you are using, the additional moment of inertia value will change. So you can do it's I2 divided by C. What is the I2 here means? The I2 here it's equal to the moment of inertia of the disk plus 2 times the moment of inertia of the small masses about its own axis, then plus the using the parallel axis theorem m time d2 square, the mass of the object time d2 square from the center of the axis or the from the principal axis. We are placing two masses, you have to twice this one. This is the new moment of inertia. Now you have to substitute this value in T2. So substituting this value in T2, this T2 it will give is equal to 2 pi square root of the I2 will be equal to I naught plus 2 times I plus 2m d2 square whole divided by the C. If you are squaring it on both sides, then the equation will be t2 square equal to 4 pi square. Square root, it will get cancelled. Then you have I naught plus 2 times I plus 2m d2 square whole divided by the C. So here you have to close this bracket. This is you have to take in the equation number 3. Now what you have to do, you have to subtract the equation, subtract 2 minus 3. This equation we are going to subtract, or 3 minus 2, whatever, that's your wish. So here what I am going to do, 3 minus 2, we can just substitute here. So first you have to substitute that 3, that is t2 square minus, if you look at the left hand side, it's t2 square, the second equation it is t1 square. So just equal to, right hand side if you look at, the 4 pi square is constant from the both the expression. You can take here 4 pi square commonly out. Now C also you can take because the denominator, the couple per unit is constant. You can take it out. Now 3 minus 2, you have to subtract everything. The third equation it is I naught plus 2I plus 2m d2 square. Now you have to minus the second one. So minus I naught minus 2I minus 2m d1 square. Just if you are subtracting, you have to put the minus in here, minus in here, minus in here. Now you have to just little bit you have to move it down further. Now the final expression, anyway, this minus I naught it will get plus I naught 2I minus 2I, it will get cancelled. 2m you can take it outside. So the final expression t2 square minus t1 square equal to 4 pi square. The couple per unit is C. You can take the 2m is commonly out. Inside you have d2 square minus d1 square. So this is the expression we have uh, here. T2 square minus t1 square equal to 8, 2 4s are 8, m pi square by c d2 square divided by d1 square. So you have to take this equation, it's the equation number 4. Now already we have the first equation, this equation number 4. The first equation tells us the empty disk, the period of oscillation square, that will be equal to 4 pi square, the I naught empty moment of inertia of the disk, there will be the couple per unit disk. This is the first equation. Now what we can do, we can divide the first equation by the fourth equation. Just we are doing that one. If I divide this two, first you need to, left hand side of the first equation is t naught square. So you got to just put the t naught square divided by left hand side of the fourth equation is just a t2 square minus t1 square. That should be equal to the left hand side of the first equation. It's a 4 pi square I naught divided by c. The left right hand side of the first equation, it's a fourth equation, it's 8m pi square by c. Here d2 square minus d1 square. Now what we have to do, you can cancel this pi square, pi square. 1 4s are 4, 8, 4, 2 4s are 8. C you can cancel. The remaining terms are, you have in the numerator only the I naught. The denominator, if you have 2m d2 square minus d1 square. We want to calculate what is the I naught, the moment of inertia of the disk, because all other quantities are we know. See here, the mass of the individual small masses, we can measure it using the weight balance. The distance is, you can measure it using the scale meter or meter scale. The time period of oscillation we can calculate using the tabular column or stopwatch. The only one unknown value, that is I naught. Experimentally we can determine. So the I naught, that will be equal to, you can, if you are keeping, then you can push it everything to the other side. T naught square left hand side, T2 square minus T1 square. You have to make the big bracket at times 2m d2 square minus d1 square. Just you go to bring this denominator to the left hand side, it will go to the numerator. So everything will be in multiplication. This is the moment of inertia of the disk. This is a way experimentally you can determine the moment of inertia of the disk. This value you can compare, the calculated value you can compare with the theoretical value, because theoretically we know what is the moment of inertia of the disk, that is equal to mass time the radius square divided by 2. You can compare whether both of them are matching. Some experimental error will be there. Anyway, all the experiment, it won't match with the theoretical value. So we can just reduce the experimental error by comparing with the theoretical value. Now, the next question one can ask, how we can calculate the moment of inertia of the sorry, the next part of this experiment, we need to know how to calculate the rigidity models of the wire using the same experiment. Yes, sir, that same tabular column we are going to use. How we can calculate the rigidity modulus of a wire. The rigidity modulus of a wire. We are going to take the same experiment, but here we are going to take that fourth equation. The fourth one we know, it's a t2 square minus t1 square. That means that with the mass at for distance d2, the time period of oscillation is t2, that square. The with the two equal masses at a distance d1, the time period of oscillation square. This difference is equal to, we have already calculated that value. It is 8 pi square m divided by the c. You got to close this bracket, d2 square minus d1 square. This is a equation. We had it in the fourth equation. Maybe once again we can check it. If you check it, yes, 8 m pi square divided by c d2 square d1 square. Yeah, this is the equation. We had it in the fourth one. Now we know what is a couple per unit twist. That is equal to uh, pi n or to the power 4 divided by 2L. This is a way we measured the couple per unit twist using the torsional pendulum. If you are just, I want to confirm once again the result. Yes, pi n or power 4 divided by 2L. Here the R is the radius of the wire, the N is the rigidity modulus of the wire, the L is the length of the wire, and the torsional pendulum. Now here we can substitute the value because we have measured the experimental T2, T1, then we can measure D2, D1, mass of the object. You can measure the radius of the wire using the screw gauge apparatus, then the length of the wire using the meter scale. The only unknown value, what is the small n, the rigidity modulus of the wire. So here the T2 square minus T1 square is equal to 8 pi square m divided by whole divided by couple per unit twist is pi, the small n rigidity modulus, r power 4, the radius of the wire, divided by the 2 times L, the length of the wire, times d2 square minus d1 square. So here what you can do, you can cancel 1 pi. This 2L, if it's going to the numerator, then it will give t2 square minus t1 square is equal to 2 8s are 16 pi m L. So 16 pi m L divided by because the 2L go to the numerator, denominator of fraction, you can invert it. The rigidity modulus time, the radius power 4 into d2 square minus d1 square. Now, if you want to calculate the rigidity modulus, so you can bring it that one side, then push this t2 square t1 square to the another side. It will give n equal to 16 pi m L divided by r power 4 into the numerator it is given d2 square minus d1 square. The denominator will be t2 square minus t1 square. This is a way you can calculate what is the rigidity modulus of the given the copper or brass wire. Here the rigidity modulus unit is Newton per meter square. Here what we have done, that's measure the T2 when we are placing the two equal masses far away from the center of the axis. Then D1 when we measure the T1 when we are placing the two equal masses near to the axis of the wire. Then so D1, D2 we can measure using the scale. So M we can measure, the length of the wire we can measure, radius using the screw gauge we can measure. So finally what we have done, we can measure all the values. So once if you know right hand side of the value, then what is the left hand side? That is a n, small n. That is the rigidity modulus of the wire. So you can just make it this rigidity modulus of a wire. This is a way you can calculate the what is the rigidity modulus of the wire using this experiment. So here in the torsional pendulum case, what we had done at the first, we measured theoretically how we can calculate the time period of oscillation using the standard differential equation. Then we have calculated the theoretically how we can measure the rigidity modulus of the wire. Then using the torsional oscillation, just now we have calculated how we can calculate, we saw how we can calculate the moment of inertia of the disk using the experimental tabular columns than the rigidity models of the wire. Everything can be measurable quantity. So this is a simple theory. Anyway, the next class, what we are going to see, we are going to do the same experiment using the virtual lab. So that is the thing we are going to try. Okay, thank you.